I'm just letting some people in from the waiting room, and looks like that's everyone for at the minute. So we will go ahead and get started. So I'm Jennifer. I am the marketing specialist here at EGI, and I want to welcome you to our first EGI webinar of our 2025 spring season. There will be 2 other webinars this season in April and in May. So I will put those details in the chat box. Today, we will be hearing from Dr. Kevin McCormick. He is our Carbon Science Initiative Director here at EGI. We will be taking questions after, so be sure to either raise your hand or put them in the chat box, and Kevin will get to them. So it looks like there's still a few more people joining us. Let's see, I'm just letting them in. Everyone who's just now joining us, I'm Jennifer, and I'm welcoming you all to our first webinar. Okay. With that, I'm going to hand it off to Kevin.
Awesome. Thank you, Jennifer. So let me share my screen. Hopefully we did this trial run just a second ago. Hopefully this works. Does that look reasonable to everyone?
That looks great.
Okay. So my name is Kevin McCormack, and I'm going to be talking about geologic carbon sequestration, geomechanics, and induced seismicity. Let's just get going. A little bit about me first. So I have a specialty in seismology and geomechanics. I did my undergrad here at the University of Utah under Professor Brian McPherson. And then I went to Stanford University where I got my PhD under Mark Zobak. And then I came back to the University of Utah at EGI to do my postdoc, which has transitioned into a research scientist role. This is the wonderful group of people that I get to work with. This is our director, or I guess I'm the director, but this is our principal investigator, Brian McPherson, who oversees everything. And these are the beautiful people that I get to work with. Very much appreciative for all the time and effort and energy that they've helped me with the science and the workload. So let's give a brief outline of today's talk. So we're going to talk about a little introduction to geologic carbon sequestration, sort of where things stand at the moment in terms of the legal aspects and the industrial aspects of carbon sequestration. And then we'll talk a little bit about induced seismicity forecasting. This is sort of you're looking at trying to understand what seismicity might take place if injection occurs. Then we'll get into the granularity of the analysis, like how detailed can we get that understanding of hazard. Then we'll talk a little bit about smaller magnitude seismicity, just a different sort of mathematical model. And then we'll conclude with a synopsis and future directions. So let's get going with the introduction. So this is a graph showing the increase of the global temperature anomaly since 1880. And you can see that the global temperature is increasing. There's debate about whether this is anthropogenic or not. And regardless of whether it's anthropogenic, there are certain strategies that we can implement to curtail these effects. So one is renewable energy. So this is wind and solar and geothermal, hydroelectric, that kind of stuff. But these technologies have been having a little bit of trouble competing against a market space that's been dominated by hydrocarbons for the last couple hundred years. And so there are other technologies that are sort of on the horizon, which are things like small modular reactors and nuclear fusion. And these technologies seem very promising, but they're still out there in the future, and we're waiting for them to be implemented. There's other things like sustainable design, which is where you look at the life cycle of a product. So you look at how the product is created, how the product is used, consumed, reused, and destroyed if needed. And that can actually reduce carbon emissions as well. And then finally, what the subject of this talk is going to be about is geologic carbon sequestration, which is where you take carbon dioxide from a power plant or a direct air capture facility, and you inject it deep underground where it stays underground, sequestered, and doesn't reach the atmosphere, not contributing to the greenhouse gas effect. The good thing about carbon sequestration is that it allows us to continue to burn petroleum responsibly. It decarbonizes the emissions from petroleum, which is actually really, really handy. So as of when I was making these slides, the Department of Energy was trying to create a new sector of the economy based around this concept of sequestering carbon dioxide. And it's unclear what's going to happen given the situation in Washington. So there has been a lot of good dialogue coming out about the benefits of carbon sequestration from both sides of the aisle. And so I'm hopeful that this work will continue. But at the moment, at the moment I made these slides, the incentive for sequestering carbon dioxide is the 45Q tax credit, which is a tax credit based on the amount of carbon dioxide that gets sequestered underground, and it's based on whether it's sequestered for EOR, deep saline, and if it's sequestered from direct air capture. So in order to get these 45Q tax credits, you have to create monitoring, reporting, and verification plans. In our group, our Carbon Science Initiative here at the EGI has been part of these. And we these plans allow the EPA to say, okay, all of the carbon dioxide is accounted for. It's not leaking. It's not causing any problem to groundwater. And we can continue. We can go ahead and allow for these tax credits. So the first thing you do in carbon capture, or CCS, is you take the carbon dioxide either from a point source, this is a power plant, a cement plant, a fertilizer plant, and you pipe it to a place of geologic significance, and you inject it underground. The other way you can do this is you can capture it directly from the air. So you can have these direct air capture facilities, which consume a lot of water and electricity. So perhaps they're not feasible for every location, but they do allow for the carbon dioxide to be captured directly from the air, which actually allows for scrubbing sectors like the transportation sector, which otherwise would not be, we wouldn't be able to scrub. So once you have those, once you have that carbon dioxide captured and you want to inject it underground, you have to ask yourself, is the geology favorable for that injection? And so you need to find a location where you have a thick, porous, impermeable reservoir that's overlain by a caprock seal that's not going to allow the carbon dioxide to escape. And you have to make sure you're not near major fault lines, and you have to make sure that you're deep enough underground that the carbon dioxide is in a supercritical state because it's much denser and easier to store in that sense. And then you have to do modeling and simulation work. You have to go through and say whether the plume is going to be X big or Y big, and whether that plume is going to interact with potential political boundaries or fault boundaries. And you have to do risk analysis. And so the subject of today's talk is going to be largely induced seismicity, and which is one of the risks associated with carbon sequestration. The other major risk associated with the other major technical risk associated with carbon sequestration is leakage. So the CO2 can leak through legacy well bores, poorly cemented well bores, or faults and fractures out of that reservoir formation and into overlying formations. And it can even take with it some of the really brackish, nasty brine that's in those reservoirs and take that up into drinking water, which is definitely a bad idea because we want to preserve the drinking water for human use. And throughout this entire process, permitting is important. You have to, there's a permitting structure called the underground injection control category. The UIC class 6 well is what allows you to inject carbon dioxide deep underground. And so we need to go through the EPA to permit and approve and issue the permit. And you need to do all of this in order to get the authorization to actually inject CO2 into the subsurface. And then once you have that, you need to construct the well such that the CO2 doesn't corrode the materials of the well, and that you don't exceed formation stresses. And you have to trap the CO2, which could be structural, residual, so it gets stuck in the pore space. Could be solubility, so it dissolves into the brine, or it could be mineral trapping, which happens over a much longer time scale, but it creates actual physical minerals. And so once you have all these elements in place, you have the permitting, you have the geologic structure in place, the simulation, you can trap that CO2 hopefully indefinitely underground. And so that's just a brief overview.
No, solo per... Allora, ho creato due.
Thank you. So that's just a brief overview of sort of the general sense of what carbon dioxide sequestration looks like at the present moment. I wish I had more information about what's happening in Washington, but it's really, I'm not sure anyone really knows at the moment. So we're just staying tuned. So let's move on to some more technical stuff, some more scientific stuff. And we'll talk about induced seismicity forecasting. So like I said, one of the big risks associated with carbon sequestration, and indeed all injection schemes. So if you're injecting wastewater or hydrogen, anything at all, any fluid at all, you're going to have issues with pressurizing the reservoir you're injecting into, which can cause poroelastic effects, stress changes around that reservoir, which can intersect with a pre-existing fracture, pre-existing fault, which can then cause an earthquake if the stresses are right. And that earthquake can interfere with infrastructure and people and humans. And we don't want this. We don't want these big events. We don't want any event really, but we don't want big events. And so we want to avoid this. And so let's talk a little bit about the mechanism by which this occurs. So when that fluid pressure propagates into the fault, the aperture of the fault, the fluid can support a little bit of the normal stress, but not any of the shear stress. It's why there's a P wave shadow zone in the Earth because those P waves, or the S wave shadow zone, right? Yeah, S wave shadow zone, because those shear waves, that shear stress can't be supported by the fluid of the Earth's core. And so the fluid can't support the shear. And so the normal stress gets reduced, the effective normal stress gets reduced, and then the shear stress stays the same, which can cause you to bring it to come closer to failure. So you bring that Mohr circle closer to the failure envelope, which can induce an earthquake. Other mechanisms exist. So you can have that poral mechanical effect. So like I said, there's this envelope around the perturbed region where you have changes in stresses given the poral elasticity, which can alter the stresses on faults and cause earthquakes. There's thermal mechanical effects where you have fluids at temperatures at the surface injected deep underground where it's hot. You have a thermal shocking effect, which can cause fractures and changes. And you can have stress transfer effects, which is where if you have a fault that slips, the region around the fault gets changed in a sort of lobed pattern, which can interact with other faults, and you can have kind of like a cascading chain reaction effect. So all of that is suffice to say that we want to avoid earthquakes. We don't want these earthquakes to occur, and we don't want these mechanisms to take place. So in order to avoid that, we need to know something about the faults that are at work. And so one way to do that is to use 3D seismic images and use edge detection and edge enhancement and tracking to figure out where those discontinuities are in the seismic volume and interpret those as faults. Another way to do that is with machine learning, where you take a UNet algorithm, and this UNet algorithm will allow you to understand where in the fault volume those discontinuities are. So you have a volume here, and you can prescribe the machine learning, and this gives you the discontinuities, the faults, the fractures as we understand them. Another way to do that is through geologic inference in the literature. So these are some faults in the San Juan Basin where we have sort of a vertical fault that we know is there because of the geology. We have these flexural faulting that must take place because of the flexural slip that's occurred because of that geology. And then we have also these faults that have been identified in the literature from other previous studies. Another way to look at this is through electromagnetic data. So this is aerial electromagnetic, I think this is LiDAR data in southern Utah, in the neck of the desert. And here we have a mapped fault, and that mapped fault seems to extend beyond where it was mapped, and we were able to determine that through that aerial electromagnetic survey. Once you have an assessment of the fault, so you identify the major faults in the region, and then once you do that, you need an assessment of the state of stress. And so one way to do that is the Simpson's coefficient or the Skits method, which allows you to take the relative stress magnitudes. This AFE parameter determines the relative stress magnitudes of the three principal stresses in regions throughout the United States. And so you take your region here, we'll just look at Salt Lake City, you take that region, and then if you assume that the stress is in frictional faulting equilibrium, then all you need is the pore pressure and the vertical stress, which are relatively easy to obtain. And that allows you to get a lower bound on the horizontal stresses. So that's one way to do it. And it gives you kind of this clean little like linear assessment of the stresses, which is nice. And so this is for that neck of the desert, which we'll talk about more in just a second. Another way to do that is with the SOSAT method, which similarly uses that frictional faulting equilibrium constraint, but this time is using it in the context of Bayes' law to actually get distributions of what we expect both the input parameters and the output horizontal stresses to be. And so now you can see we have these error bars. We have uncertainty confidence intervals of the stresses. And so the other way to do this is with the hybrid method, which is where you use the linear elastic approximation, which is controversial in the literature. But you use that linear elastic approximation to get a first estimate of the stresses. You rotate that stress onto a fault plane that's ideally oriented in the stress field. You calculate the shear stress on that fault plate. You compare it to the peak strength of the rock, which you obtain through correlations, petrophysical correlations. And then that gives you a sense of whether the rock is in failure, in which case you use the frictional failure equilibrium, or in a linear constraint, in which case you use the linear elastic approximation. And so that's a third method to obtain the stresses. So now we're going to look at this application taking the faults plus the stresses in two different examples. The first is the neck of the desert, which I've been talking about, and this is the Iron Mountain project, where there's an iron mine that wants to create a direct reduced iron plant, which has a byproduct of carbon dioxide. And so that byproduct of carbon dioxide, they want to dispose of responsibly, and they want to inject it underground. And so I was doing some analysis of the potential induced seismicity of that work. The other place we'll be looking at is the San Juan Basin. This is in the Four Corners region. And this is a project where they have a power plant that wants to sequester carbon dioxide, and they have multiple wells or they're planning on drilling multiple wells that will inject the carbon dioxide in large quantities. We're talking tens of millions of tons of CO2 over the course of 12 to 20 years. And so these are the two projects we'll be talking about, and I'm just going to compare them side by side as we see this workflow. So in the neck of the desert, one of the first things you want to do is you want to look at the past seismicity. You want to look at what seismicity has occurred previously. And so in the neck of the desert, we see that there's actually quite a lot of seismicity that took place, which is cautionary. We want to be careful about that. And it's occurring mostly away from the injection zone, but it's also occurring near the injection zone. And so that's just a cautionary tale. In the San Juan Basin, we have seismicity in the past that's occurred a little bit in the region of interest. This green box is the region of interest, but most of it occurs sort of in the periphery of the basin, where there's sort of more geologically complex structure, as opposed to the flat-lying sediments in the interior of the basin. So it's very beneficial to look at the past seismicity to make sure you're not in a region that's just like screaming seismogenic. And then what you do is you take those stresses and those faults that you obtained previously, and you perturb the input parameters in a Monte Carlo sense. So you have the stresses and the faults, which give you about 8 input parameters in total, and you perturb those in a Monte Carlo sense, and you run it about 10,000 times per faulting scenario. And you end up with a distribution of Coulomb failure functions. Now, the Coulomb failure function is the distance from the pole to the failure line. That's sort of an assessment of the geomechanical stability of the fault. And so you run this 10,000 times. So in the case of the San Juan Basin, we ran it for the basement fault 10,000 times, the vertical fault 10,000 times, flexural fault, and Dakota faults. For the neck of the desert, because we didn't understand, or we didn't have information on the dip of the fault, we didn't know what the dip of the fault would be. We ran it on different dip distributions for sort of 45 degrees, 60 degrees, etc., trying to analyze what the impact of the dip would be. And now once we have that distribution of Coulomb failure functions for each of those faulting scenarios, we can plot up those distributions. And so now we have the Coulomb failure function on the left-hand side. And these are the dip scenarios that we assessed. And so in this in the neck of the desert, it's evident that the dip plays a huge role. If the dip is 75 degrees or more, the Coulomb failure functions are saying that fault should slip. Now, it does matter whether that fault penetrates to depth. It matters if the fault penetrates deeply enough into the reservoir, but it does seem like it's amenable to slip if the dip is high. So the dip is really important. And then for the San Juan Basin, those scenarios that I just said, we have one scenario where it's slightly problematic. And so we want to investigate that further. We want to look at that flexural scenario. So let's look at this flexural faulting scenario right here, this shaded gray area. So this has been a region that's experienced a lot of saltwater disposal, 20 million barrels of saltwater disposal in the last 15 years or so. And there hasn't been much seismicity. There really hasn't been much detected seismicity because of that, even though we're saying that, and it's been into the exact same formation that the proposed carbon dioxide should be into. So there hasn't been much seismicity from the injection of 20 million barrels. And so we think that maybe what's going on here is that because of the nature of the flexural faulting, these faults are sort of these subparallel flexural faults where they flex and they slip, causing discontinuities. And so instead of being like one big fault that can host a big earthquake, the seismicity is actually getting distributed, or at least that seismic motion is getting distributed across all of these faults, which is causing much smaller earthquakes to take place that aren't being detected by the network at place. So let's just, and then the other good thing about this method is that it allows you to look at the sensitivities of the input parameters. And so for the neck of the desert, it's clear that we knew this going in, but it's good to verify it, that the dip of the fault is the big sensitive factor. We really need to constrain that dip of the fault before we move forward with the project. In the San Juan Basin, the dip is also very important in all of the scenarios, but there are also other key elements such as the coefficient of friction or least principal stress. So that was the induced seismicity forecasting. I'm going to take a quick sip. Okay, so let's get into the granularity of analysis. So this is sort of something that occurred to me where I was looking at, like, fault planes aren't just planes. It's not just a plane. Although oftentimes in the literature, they're approximated as just planes, just a mathematical plane. And so in reality, we know that they have roughness, they have rugosity, and they have curvature. But can we model that mathematically? And so what I did was I took the hogback flexural faults, those same faults that we were talking about with the injection and the distribution of slip. And I looked at those faults and I plotted, I sort of meshed them in a hexagonally, closed pack hexagonal spheres in order to attribute different regions of that fault to each sphere. So that way you can see that because the fault curves, you have different You have different strike and dip here than you do here. And so mathematically, I can encapsulate that by looking at this discretization method of the hexagonally closed packed spheres. I incorporated Bayes' law to take data from this x sub j is the data of the location of that fault plane, and you use a Bayesian regression to from that determine the dip and the strike for each of those enmeshed spheres. And then you incorporate the state of stress, which is right here, these orange curves, into the geomechanical model. And what you get is a distribution of Coulomb failure functions for each of those spheres. Now, when we plot up the results for a single plane, we have this uncertainty. So the red corresponds to the uncertainty from just the state of stress, so assuming that the plane is fixed. And the blue is the total uncertainty of the model. And now you can see that as we have a big mesh, we get this uncertainty. As we have a medium mesh, we get this uncertainty. And as we have a small mesh, we get a very different uncertainty. And what's going on here is overfitting. So if the mesh gets too small, the spheres are too small, then what ends up happening is that the statistical significance of the data within each of those spheres becomes lessened, and we get greater uncertainty. And so instead of looking at this discretization method with the enmeshed closed packed spheres, instead what makes more sense is to look at the Krieged volume. So you use Gaussian processes to assess what surface incorporates all of the data, but interpolates between them, which is a Kriegung effect. And so this allows us to get a minimal amount of uncertainty, but also a maximum amount of granularity. And so these are the data for these are the results of the Coulomb failure function for the big discretization, medium discretization, and small discretization. And you can see that they're all sort of highlighting a region on the fault that seems to be of higher hazard. And then this is the effect from that Kriegung effect. So now instead of looking at three-dimensional space, the z-axis is the Coulomb failure function. But the good thing about the Kriegung is that we now have these error bars. We have these confidence intervals, which are very handy. And so the main takeaway from this point is that the hazard that you see on the fault is a function of location on the fault. And that's what I really want to point out, is that, you know, the hazard is different here than it is here. The hazard is different here than it is here. And that's the big point, the big takeaway of this. Now, when we apply that to the San Juan Basin, so we took a state of stress. So we used all three of those states of stress methods, the skits, the SOSAT, and the hybrid. And we populated two different states of stress, one based on the more shallow data and one based on the deeper data. And the reason for that is just that we had different petrophysical data for those two regions. And so it just made sense to separate it. So we're going to look at this fault 31, and then we're going to look at all of the faults using these states of stress. So first, let's look at fault 31. So fault 31 is this surface here. So these blue points correspond to the ant tracking picked locations of the fault. So these are locations in the 3D seismic cube that the ant tracking says, aha, there's a discontinuity. And so that's what these blue points are. And then this pink curve, this pink surface, is the Krieged surface through those points. The star is something for the paper. Please don't worry about that. So what do we see here? We have the skits, the SOSAT, and the hybrid stress states. And we see that all three of them agree that this fault in general is close to failure. It's red, it's got a high Coulomb failure function. They also agree that this region right here corresponds to a relatively low hazard region. And there are some subtle differences throughout that change from fault to fault, or from stress state to stress state. And then, but the main takeaway here is that the hazard assessment is not terribly different between the states of stress. It doesn't seem to change much. And so this is all of the faults. So now we're looking at all of the faults, and this fault 31 is up here and up here. And for the hybrid data, we didn't have as much coverage and depth as we did for the other two approximations, and so we weren't able to assess the entire suite of faults. But we can see something similar that we just saw, which is that the faults are being highlighted very similarly between the states of stress. There are more differences now than there were with the single fault, especially the intensity of the color here versus here, which corresponds to less hazard. Also, when we look at the Coulomb failure function distributions between the three states of stress, we see that the Coulomb failure function distributions are different. And so there's a statistical difference between these states of stress. And so for me, the conclusion I draw from this, and this is interpretation, and so you're welcome to disagree, but for me, the conclusion I draw from this is that the state of stress, the method of determining the state of stress should be determined based on the parameter, the data available, and the requirements of the project, right? So some projects may really like how quickly you can determine the state of stress using the SCITS method. Some projects may like the fact that you can incorporate uncertainty and error bars in the SOSAT method. Other projects may like that you can incorporate sort of the constitutive nature of the rock in the hybrid method. So that's the takeaway I have from this. But again, it's open for interpretation. Okay, and then now we're going to move on to smaller magnitude seismicity. So we're going to be looking at an EOR site in Farnsworth, Texas. This is the panhandle of Texas. It's a 5-spot pattern oil site, and there are a couple injectors and a lot of producers, injectors of carbon dioxide. And we're going to be looking at a seismic array that was downhole that was measuring seismicity for this project. So this is the seismicity that was measured. So they've been injecting carbon dioxide for about 10 to 15 years, but they only were recording, sort of keeping careful records starting in 2019. And so the blue corresponds to the seismicity, and the moment magnitude is given by the y-axis. This is the largest earthquake here in blue. And then you can see these, and then this red curve is the injection. So the injection that's taking place is given by the red curve, and you can see that it's pretty much constant throughout the lifetime of the field. And you can see this series and this series of seismicity, which corresponds to what we believe are runaway ruptures. This is where you have a single fault plane that's rupturing in multiple locations repeatedly throughout the duration of the injection. And that's not good, because that could lead to a larger rupture. So we don't like to see that, but we do see it in these two cases. So we have about 1,000 earthquakes and a magnitude of, with a number above the magnitude of completion of about 200. So we're going to do some maximum magnitude predictions. So these are equations that I'm about to show you that allow you to assess what is the maximum released energy you would expect to see from the injection that's taking place. So there's the uncalibrated moment cap, the calibrated moment cap, the statistical method, and the residual method. Now, all of these equations are based on two factors. I mean, there are multiple factors, there are many factors, but there are two fundamental factors that are taking place here. One is the injected volume, this delta V, and that's as a function of time. And then the other is the release of moment. And there's not a good mathematical symbol to represent that other than maybe this guy. The release of moment. So how much, so it's a counterbalance between how much fluid is being injected and how much seismic energy is being released. Because you imagine if you inject a ton of fluid, you'd expect larger seismicity, or if you imagine you release a lot of seismicity, you'd expect smaller seismicity. So what do these curves look like in sort of mathematical space? So what you're looking at is time on the x-axis and the magnitude of the earthquakes on the y-axis. The orange dots correspond to the earthquakes, and these curves, this blue, red, purple, and green, correspond to these curves, these mathematical interpretations. And so ideally what you would like to see is you'd like to see a curve that bounds the seismicity more or less perfectly. It just perfectly fits over the seismicity, which is not what we see. And so what we set out to do is we wanted to improve upon these mathematical models. We wanted to get a model that better bounds that seismicity. And so what we did was we plotted these 4 literature models for our site, for our seismicity site, our EOR site in Texas. And you can see here, this model actually breaks down when we get to one of those runaway rupture events. And the reason for that is because the seismic release exceeded the injected volume. And so mathematically, that was taking the log of a negative number, which obviously you can't do. And so this model breaks down. But regardless, we see that these models are doing a pretty good job of fitting the data, but it could be better. It could be better. And so we're going to try an improvement. So the improvement we decided to try is we tried to look at the Gutenberg-Richter B value. And so this Gutenberg-Richter B value is the slope of the line that's plotted when you plot all of the magnitudes in magnitude versus log number space. And so what we're doing is we're going to do this dynamically. So every time an earthquake occurs, we're going to recalculate that line. We're going to recalculate the B value to give us a better approximation of what the seismic rate is at the time of the earthquake actually taking place. And so what this looks like is in absolute time from July to January, we have the B value changes from each of the events that take place. But since most of the events are concentrated here, it's actually more illustrative to look at the index of the earthquake. So just each earthquake individually. And so you can see in general, the B value is increasing because most of the earthquakes taking place are very small. And so those small earthquakes you would have a higher B value. But then when a large earthquakes, or in this case, 2 large earthquakes take place, you have a decrease in that B value. So you have a dynamic assessment of the B value. Now, what happens when we plot up that seismicity curve, or that Mmax curve? So what you end up with is you have the original curve in red here. This is just using a single B value from the catalog versus the dynamic B value. And it looks like we do a better job of capturing the seismicity. It looks like this event maybe was under captured. We like that this comes up at this point. And so maybe we've done a better job of incorporating the seismicity. Now, this is one way to look at it, but there's also sort of a food for thought to think about here. And that is, what about a composite model? So we have all of these mathematical models. They have varying assumptions, varying input parameters, varying physical realities. But what would happen if instead of just looking at a single model, you used a misfit criterion between what you're seeing in the models, but what you're seeing between the earthquakes actually happening and the models that you've calculated. So you've changed that model based on the earthquakes that take place. Now, in my opinion, you would want to, the ideal situation is you have one model that fully incorporates all of the physics. All of the physics are incorporated, and it's the most realistic, sensible model. But I'm not sure we have that or even close to that. And so maybe this composite sense with this misfit criterion is a reasonable way to go about it. I'm not sure. It's just sort of food for thought. Okay, getting on towards the end, we have synopsis and future directions. So all of what we've been talking about well, almost all of what we've been talking about is based on the concept of merging a state of stress and a fault orientation. And so if we have better states of stress and better fault orientations, surely that would reduce the uncertainty in the hazard that we predict. And so this is just a sense of how we can incorporate petrophysical data into the state of stress to get a better assessment of the stress. And then there's also things in the literature. This is from one of my early papers, looking at the viscoelastic stress relaxation of formations, which may be able to better inform the state of stress, and also having data like extended leak-off tests, DFITs, mini-frac tests. All of that is great. And so really, really constraining the state of stress. On the other hand, those fault orientations may be possible to understand them better if we look at sort of bigger picture statistical view of a basin. So we have sort of the evolution of a basin that takes place through time. So this is depositing and deforming through time. And during that time, if we model that carefully, we may be able to figure out where those fractures take place and what orientations you might expect those fractures to take place at. So for instance, during this period in time, maybe you'd expect the fractures to be mostly north-south with a dip of 30 degrees or whatever. And so what that would allow you to do is create a statistical sense of what you think the fractures are in the region, because there's no way the seismic modeling, the UNet, the geologic inference, there's no way you can fully assess all of the fractures and faults. And so this will give you a statistical sense by which you can sort of account for the fact that you haven't accounted for everything. And then the thing that's really missing in all of this is field validation. We don't really, these projects aren't really injecting right now. They haven't really begun. Not many anyway. And so what we really need from this, sort of like the holy grail of my research would be to take earthquake locations from actual injection sites and show that there's a statistical preponderance of those earthquake locations on the red portions of the faults. So that's where the hazard was said to be higher. If we can show that the earthquakes are actually taking place on those locations of higher hazard, that would be fantastic. It would be field validation, which is needed in this research. And so I'm just going to leave you here with this sort of summary of what we've talked about, which is essentially we take faults through various methods, apply a state of stress, and have a granular understanding of hazard in the subsurface. And so the idea here is that the operators would then be able to look at the region they're injecting into, and they may be forced into a certain region through pipelines or political boundaries or who knows what not. They may be forced into a certain region, and they may be able to inject with more confidence that whatever faults are present either have a low or high hazard, and they have an understanding of that hazard. And so with that, I thank you very much, and I'll take any questions.
You can either leave questions in the chat, or you can use the hand raising question or option, or you can just unmute yourself.
Hello, hi. It's Romain Prieur. Can I ask a question?
Yeah, of course.
Thank you very much for your very informative talk. I think it's very, very good. I had a question about the composite model for the magnitude versus time. I mean, I think it can be used. It seems to be useful tool to explain the data in a post-mortem fashion. But how would you use it if you want to use it as a forecasting tool?
Well, I guess the way I would answer that is that you have a misfit criterion in the past 50 earthquakes, like you said, in the past, which would dictate which of the models is currently being assessed. And so you have 4 or 5 models, And right now you're using the moment cap model. And so that's the model that you would use for the forecasting until it becomes violated, at which point you would switch to a different model. You're right, the forecasting is harder in this sense.
Okay, yes. All right, okay, thank you. Yeah.
Yeah.
Hi, Kelvin. Thank you for your presentation. This is this is Anthony here. I wanted to know if you can explain the thermomechanical effect of the CO2 injection on the seismicity again.
Oh boy, I'm not to be perfectly honest, I'm not sure I can. So basically when the fluids are at temperature at the surface, it's a different temperature than deep underground. Deep underground is typically hotter. And
Yeah.
so when you inject them, there's like an equilibration that takes place between those two temperatures, and that causes changes in the mechanical stresses, can cause fractures. I'm not an expert on thermodynamics. I'm sorry.
Okay. All right. That's fine. Thank you.
Looks like there are a few questions in the chat box
Oh.
here. Kevin, are you able to see them?
How do I? Can you read them to me, Jennifer?
Definitely.
Thank you.
From Robin Lynch, how do fluid properties affect the risk, such as pronounced water versus CO2? How comparable is saltwater injection data to potential CO2?
Yeah, that's a great question because obviously CO2 has a greater compressibility than water. And so if you're injecting water, you'd expect the pressurization to be higher. So the mathematics that I've shown here are all based on the absolute pressure / stress perturbations. And so the what would happen is that the values you'd be interested in my calculations would change based on the fluid that's being injected. But I actually really want to do more research on that. That's one of my ideas going forward, is to look at the sort of really quantify the change in hazard based on different injection fluids. For like you said, salt water, if you inject the same amount of salt water as carbon dioxide, you'd expect the salt water to induce more earthquakes for sure. I agree with that.
There's another one I can read to you, Kevin. This is from Paul Dennick. Could you reduce stress in a region first by using injected water in some places to encourage slip, removing water in other regions to cause pinning, then go back to a stress relieved area to inject supercritical CO2?
I don't see anything immediately wrong with that. I think it's a lot of geoengineering. I mean, it's there's a lot of uncertainty in geoengineering. But I think the idea at least is sound, that you can release the seismic moment, and then have a safer location to inject into. I think I want to think about that more. I don't want to say too much right now because that's a really interesting thought that I really like, and I want to think about it before I really give any opinions. I like it though.
See any others in the chat box?
Did you say there's nothing more in the chat box?
There's nothing more in the chat box.
Okay. Well, I guess in that case, if everyone's content, I'm content. Enjoy your Thursday, and thank you very much.
Thank you everyone for joining us, and sign up for the other upcoming webinars. Thank you, Kevin, again.
Thank you.
Thank you. Bye, everyone.